Okay, so at the previous lecture we introduced nuclear operators. So this is a very important class of operators. It's important for many reasons. For example, nuclear operators of trace 1, positive nuclear operators of trace 1 between Hilbert spaces naturally appear as quantum mechanical states. But for our course, nuclear operators are important because they are involved in the definition of nuclear locally convex spaces. So let's recall some definitions related to nuclear operators. First of all, we define nuclear operators in the case where the operators act between Banach spaces. So if E and F are Banach spaces, then we have a natural map from the projective tensor product of F and the dual of E to the space of continuous linear operators from E to F. And this map gamma is uniquely determined by the following rule. It takes every elementary tensor, Y tensor F, to the following rank 1 operator. And this map is well defined and continuous. This easily follows from the universal property of the projective tensor product. We simply linearize the obvious bilinear map for the completed projective tensor product. And we say that a linear operator f phi from E to F is nuclear if it belongs to the image of gamma. We gave several equivalent characterizations of nuclear operators between Banach spaces. In particular, we proved that a continuous linear operator between Banach spaces is nuclear, even only if it is the sum of an absolutely convergent series of rank 1 operators. This implies in particular that every nuclear operator is compact, but not the other way around. So when we discussed diagonal operators on LP spaces, we observed that they are compact, recalled from the extended functional analysis course, that they are compact even only if the respective sequence vanishes at infinity, and on the other hand, they are nuclear. Such an operator is nuclear if and only if the respective sequence is absolutely summable. So nuclear operators, the class of nuclear operators is strictly smaller than the class of compact operators. So this is the class of Banach spaces, nuclear operators between Banach spaces. In the locally convex settings, the definition is as follows. You have two locally convex spaces, X and Y. Then a continuous linear operator phi from X to Y is nuclear if there exists a commutative diagram of the following form, where E and F are Banach spaces and psi is nuclear. Phi is nuclear if there exist Banach spaces E and F and a nuclear operator psi from E to F such that the diagram commutes. And script n is the standard notation for the space of nuclear operators between E and F. We consider some elementary properties of nuclear operators. In particular, we put the following characterization. Let's recall the statement. Proposition. So the following conditions are equivalent. If phi is a continuous linear operator between x and y, then the following conditions are equivalent. Condition 1, phi is nuclear. Condition 2, phi can be written in the following form. Sum of the following series, where lambda n is an absolutely summable sequence of numbers. Fn is an equicontinuous sequence of linear operators on x. Equicontinuous. And Yn is a sequence of elements in Y, which is contained in some Banach disk. Where B is a Banach disk in Y. Banach disk means that if we consider the linear span of B and equip it with the Minkowski functional, then the resulting semi-normed space will be a Banach space. And condition 3 is a condition of this form, but now we can construct E and F explicitly. So there exists a continuous semi-norm P on X, and there exists a Banach disk B and Y. There exists a nuclear operator psi between the associated Banach spaces X, P tilde and Y, B, such that the following diagram commutes. So this is phi from X to Y, this is X, P tilde, this is Y, B, and this is psi. And here we have the canonical maps pi p and j b. So this diagram commutes. Well, let's recall what pi p is and what jb is, because we will need this construction today once again. So let's recall that if p is a continuous semi-norm on x, we denote by xp the quotient of x modulo the subspace where p vanishes. So we consider this quotient as a normed space with respect to the quotient norm of p. So this is normed space, and xp tilde is the completion of xp. And pi p is just the quotient map. Pi p, x from x to x p tilde, by the following simple formula. So YB, well, I've already said that YB is the linear span of B. And JB is just the inclusion map. And we always are Y, not X, but Y. JB is just the inclusion map of YB into Y, and let's also recall that we always consider YB as, well, B is a Banach space, so this is a Banach space with respect to the Minkowski functional of B. Okay, so this is our main characterization of nuclear operators between locally conic spaces. Let's now look at some properties of nuclear operators. A nice property which will play an important role today later is that every nuclear operator factorizes through a Hilbert space. So if x and y are locally common spaces, and phi is a nuclear operator from x to y, then there exists a Hilbert space H, and the continuous operators alpha from x to h, beta from h to y, such that phi is beta alpha. To prove this result, we may assume from the very beginning that x and y are Banach spaces. Because, well, if we factorize this map through a Hilbert space, then this one will be automatically factorized through the same space. So we may assume that x and y are Banach spaces. X and y are Banach spaces. And let's write phi in the following form: sum over n, lambda n, fn, yn, where fn is a bounded sequence in x prime, yn is a bounded sequence in y, lambda n is summable, and without loss of generality, we may assume that lambda is non-negative. Just by multiplying, say, yn by suitable numbers, we may assume that lambda n is non-negative. Let's now construct h. So what is h? H will be just a little O2. And we define alpha from x to L2 by the following formula, alpha of x. So this should be a square summable sequence. This will be the following sequence, the square root of lambda n, fn of x. So clearly this is square summable because of this property and because fn is bounded. And we define beta from L2 to y as follows. Beta of Zn, so Zn is a square summable sequence. So beta of Zn is the sum of the following series: lambda, the square root of lambda n, Zn, yn. Since lambda n and Zn are square summable, it follows that this one, lambda n Zn, is absolutely summable. So this series and yn is bounded. So this series converges absolutely in y and gives us a map beta from L2 to y. Now it's almost immediate from the construction that alpha and beta are what we're looking for. And it's also elementary to an elementary estimate shows that beta and alpha are bounded. And alpha are bounded. And that's it. Another useful property of nuclear operators is that the class of nuclear operators is stable under projective tensor products. You have two nuclear operators, phi1 and phi2. So phi kx from xk to yk. Then their uncompleted projective tensor product and their completed projective tensor product are nuclear operators. And the second part of this proposition states that the dual of a nuclear operator is nuclear. If phi is a nuclear operator from X to Y, then the dual operator phi prime is a nuclear operator between the strong dual spaces Y prime beta to X prime beta. So let's recall that the strong dual space is, by definition, a dual space equipped with a topology of uniform convergence on all bounded sets. In particular, in the special case of normed spaces, this is just the usual normed dual space. The proof is a simple exercise for you. In fact, everything is easily reduced to the case of bounded spaces. First, reduce to bounded spaces, and in the case of bounded spaces, everything readily follows from the definition of a nuclear operator. The initial question is, how about the opposite implication, which is, of course, this question, of course, comes from the classical Schroeder's theorem, which states that a bounded linear operator between bounded spaces is compact, if and only if, in both directions, if and only if the dual operator is compact. So can we replace here compact by nuclear? Surprisingly, this question was an open problem for about 20 years. Eventually, a counterexample was found. So a warning. If phi is a continuous linear operator from X to Y, and phi prime is nuclear, this does not imply that phi is nuclear. The counterexample, the first counterexample, was found by Fiegel and Johnson in 1973, and it is closely related to the approximation property. And another warning is the following. Suppose we have a nuclear operator phi from X to Y, and suppose that the range of phi is contained in a closed vector subspace. Z is a closed vector subspace of Y, such that phi takes X to Z. So we can consider phi as a map from X to Z. It turns out that this map from X to Z is not necessarily nuclear. This doesn't imply that phi is a nuclear map from X to Z. A bit surprising, but that is life. By the way, this counterexample is not so hard. I'll probably include it into the respective exercise sheet. Fortunately, in the special case where our spaces are Hilbert spaces, such pathologies are impossible. So let's prove the following useful proposition. Suppose we have Hilbert spaces x1 and x2, Hilbert spaces, and the nuclear operator phi from x1 to x2. And suppose we have two closed vector subspaces, y1 in x1 and y2 in x2, closed subspaces. And let's also assume that phi takes y1 to y2. Then we can consider the following picture. So this is our operator phi. We can restrict it to y1, and we get an operator from y1 to y2. And here we have the inclusion maps. And let's denote the restriction of phi to y1 by phi1. We can also consider the quotients, x1 modulo y1 and x2 modulo y2. And here we have the induced map phi2, which acts in the obvious way. And here we have the quotient maps. I claim that both operators phi1 and phi2 are nuclear. Well, why is it so? Well, let's denote the inclusion maps, say by y1, y2. So these are inclusion maps. And here we have quotient maps, q1 and q2. Well, y2 is a closed subspace of x2, and x2 is a Hilbert space. So we can consider the orthogonal projection, as denoted by P. So there exists a continuous linear map P such that Pi2 is the identity map, just the orthogonal projection. Then our map phi1 can be written in the following form: phi I2 phi1. Now I2 phi1 is, so the diagram is commutative, so this is phi composed with I1. But phi is nuclear, and the composition of a nuclear operator with arbitrary continuous linear operators is nuclear. So this shows that phi1 is nuclear. How about phi2? Here we use the classical fact that the quotient of a Hilbert space modulo a closed vector subspace can be isometrically identified with a subspace of x1. So in other words, there exists a continuous linear map J such that JQ1 is 1, is the identity map. And this implies that phi2 can be written as follows. Phi2 is phi2 composed with JQ2 and phi2 Q1, of course. JQ1. Well, sorry, that's wrong, of course. In that first we apply J and then we apply Q1. So the correct formula should look like this: Q1 J. So now we substitute this map here. So phi2 is phi2 Q1J. Phi2 Q1 is Q2 phi. Q2 phi J. Phi is nuclear, and so this map is also nuclear. And this completes the proof. Well, actually, if we look at the proof of this result, we can easily observe, remark for those of you who are familiar with the notion of a complemented subspace. So the same proof, the proof actually shows the following. It shows that if x1 and x2 are just locally convex spaces, x1, x2 are not necessarily Hilbert spaces, but are just locally convex spaces. And if y2 is complemented in x2, then phi1 is nuclear. Y2 is complemented in x2, then phi1 is nuclear. And if y1 is complemented in x1, then phi2 is nuclear. Okay, but we will later use this result in the special case of Hilbert spaces. By the way, by the way, if we come back to this warning, we see that to find a counterexample here, where is it? To find a counterexample here, we must take something which is not complemented. So the counterexample is based on the existence of uncomplemented subspaces. Okay. Okay, so now we are ready to introduce nuclear spaces. The definition is very short. Actually, there are many equivalent definitions, and we'll discuss only some of them. But the shortest definition looks as follows. We say that locally convex space E, or locally convex space X, is nuclear if for every Banach space E, all continuous linear maps from X to E are nuclear. All continuous linear maps from X to any Banach space all continuous linear maps are nuclear. Well, first of all, let's look at the trivial example and the trivial counterexample.
Nuclear spaces seems rather small.
Yeah, in some sense they are small. Trivial example is that finite dimensional spaces are obviously nuclear. X is finite dimensional, then X is nuclear. For the obvious reason that any continuous linear map of finite rank is nuclear. This follows, for example, from our characterization of nuclear operators. So clearly, if phi is a finite rank operator, they can always write it as a finite sum of this form. So a finite rank operator is always nuclear.
Excuse me, what will abort it in this characterization in terms of absolutely convergent series when we go to subspace? Что может нарушиться, когда мы переходим в подпространстве?
You mean this yeah. Well, Yn are not in the same subspace. They are in the bigger space. So the point is that we cannot adjust Yn in such a way that they sit in the same subspace where the range of phi sits. They are in the bigger space. That's the problem. So anyway, if X is finite dimensional, it is obviously nuclear because finite rank operators are nuclear. And an obvious counterexample, an infinite dimensional Nernst space is not nuclear. Well, indeed, if we consider the inclusion of X into its completion, it's an isometric embedding, so it is not nuclear. Actually, it is not compact. It's not compact, so it is not nuclear. We will see shortly that there are many natural examples of nuclear spaces. In some sense, the class of nuclear spaces, on the one hand, it is very nice. Roughly speaking, in many concrete situations, nuclear spaces behave like finite dimensional spaces. But on the other hand, the class of nuclear spaces is very big, and we will see this shortly. But before this, let's give some equivalent characterizations of nuclear spaces. So let's recall the following construction. If you have a locally convex space X, and two continuous seminorms on X such that P is dominated by Q, we can always draw the following picture. So we have the associated bounded space XP tilde and the associated bounded space XQ tilde. So here we have canonical maps pi P and pi Q. And we can always construct a unique continuous linear map pi PQ from this space to this space such that the diagram commutes. This construction was already used when we discussed the completion of a locally convex space. Actually, the projective limit of the resulting projective system is nothing but the completion of X. And explicitly, pi PQ is uniquely determined by the following formula. This formula defines pi PQ on a dense subspace of XP tilde, which was denoted by just XP, or sorry, XQ, and then we extend it by continuity to the completions. Okay, so let's now look at the following characterization of nuclearity. Suppose that X is a locally convex space, and let P be a directed defining family of seminorms. On X. When the following conditions are equivalent. Condition 1. X is nuclear. Condition 2, for every P, for every seminorm P in our family, the canonical map pi P from X to XP tilde is nuclear. So in other words, we don't have to consider all bound spaces. When we work with nuclear spaces, it's enough to consider the bounded spaces XP tilde. Condition 3, let me here, condition 3, for every P, seminorm P in our family, there exists another seminorm Q in our family such that P is dominated by Q, and such that the respective map pi PQ, which acts from XQ tilde to XP tilde, is nuclear. So again, we see that everything is reduced to bounded spaces. So X is nuclear if and only if this map between bounded spaces for a suitable Q, depending on P, is nuclear. Well, the proof. So before we prove this result, let's look at the following simple lemma. Suppose that E is a bounded space, and phi is a continuous linear map from X to E. I claim that phi actually factorizes through one of the bounded spaces XP tilde. There exists a seminorm P in our family, and there exists a continuous linear map psi from XP tilde to E, such that the following diagram commutes. This is phi from X to E, this is XP tilde, this is psi, and this is the canonical map pi P, such that the diagram commutes.
X is nuclear? Yeah.
No, X is an arbitrary locally convex space, X is an arbitrary locally convex space, and P is a directly defining family of seminorms. So X and P as in our proposition. So we don't assume X to be nuclear, an arbitrary locally convex space. The proof is very easy.
Yeah.
The proof is very easy, actually. We define a new seminorm on X as follows. This is a continuous seminorm on X. And so, since it is continuous, it is dominated by a suitable P. There is a seminorm P in our family. Well, formally there are finitely many seminorms, but P is assumed to be directed. So there is a single seminorm in P such that this seminorm is dominated by P. And so to define psi, we first define it on xp without tilde, just the quotient of x modulo the subspace where p vanishes. And we define psi by the following formula. And this property implies that psi is well defined and bounded. Well defined and bounded. So it uniquely extends to the completion. And that's it. Okay, so now we can prove our proposition. First we prove that 1 implies 3. So we assume that X is a nuclear, and we prove that for every P we can find Q such that this map is a nuclear. One implies 3. So again, let's draw a suitable picture. This is X. This is X P tilde. This is pi P. So to find Q, we want to find Q such that the map from Q tilde to XP tilde is nuclear. Well, so by assumption, pi P is nuclear. And we know that, so by definition, we can factorize pi P through a bounded space, E, such that this map is nuclear. Just by the definition of a nuclear operator between the locally convex spaces. And then we apply our lemma, and we factorize this map through a suitable XQ tilde. So this follows from lemma, and this follows from the definition of a nuclear operator. Okay, so now we have the following picture. The composition of these two maps makes the full diagonal commute, and there is only one map which makes the diagonal commute. This is pi pq. So we see that pi pq is the composition of two bounded linear operators, one of which is nuclear. So pi pq is nuclear. And this shows that 1 implies 3. 3 implies 2. So now we assume that for every P there is Q, such that this map is nuclear. We want to show that pi P is nuclear. But pi P is, again, a composition of two arrows, this one and this one. Pi P is pi PQ composed with pi Q. Pi pq is nuclear by assumption, so pi p is nuclear. And finally, y2 implies 1. So we now assume that all maps pi p are nuclear, and we want to show that every map from X to any bounded space is nuclear. We simply apply our lemma. So this one is nuclear, and this implies that phi is nuclear. So this was from lemma. Okay, so this completes the proof. As a corollary, we see that a locally convex space X is nuclear, even only if its completion is nuclear. For the simple reason that the associated Banach spaces, the Banach spaces associated to X and to X tilde are the same. And the respective maps pi pq are the same. Okay, let's have a look at some examples of nuclear spaces. Example 1. The simplest and trivial example is a space of all functions of an arbitrary set with the product topology k to the power s, where s is any set. So I claim that this space is nuclear. And why is it so? It is nuclear because all the associated Banach spaces are actually finite dimensional. KSP is finite dimensional for every continuous seminorm P. Well, indeed, the standard defining family of seminorms is just the absolute values of pointwise evaluations. It is not directed, but we can add finite maxima. So for every finite points, we consider the maximum of, if f is a function, we consider for every finite family of points x1 to xn, the maximum of the absolute values of x of f1 up to f of xn, and the respective, after we quotient out the subspace where the seminorm vanishes, we get something finite dimensional. And that's it. So all operators between finite dimensional spaces are nuclear. So this space is nuclear. To construct other examples, we will need the following result, the following general proposition, the so-called Grothendieck-Peach criterion. The Grothendieck-Peach criterion. This criterion, this is a nuclearity criterion for Curtis sequence spaces.
Может, пока мы далеко совсем не увидели. А вот это Е, я что-то пропустила, что это такое.
Оно существует по определению ядерного оператора между локальными и пространствами. So,
да, все, окей.
So by definition, continuous linear operator between locally convex spaces. So this is a locally convex space and this is a locally convex space. This one is a Banach space, but at this point we look at it as a locally convex space. So this operator acts between locally convex spaces, and by definition, it is nuclear if it factorizes through a nuclear operator between Banach spaces. Mm-hmm. So formally we'll have to add two spaces E and F, but we compose the map from E to F and the map from F to X to tilde, and this error is also nuclear. Okay? So this comes from the definition of a nuclear operator, and this one comes from M. Okay, so the Grothendieck-Peach criterion gives us a nuclearity criterion for Curtis spaces. So suppose that I is in a set, and P is a Curtis set of I. That is a set of non-negative functions satisfying some natural conditions of it is directed and in some sense not degenerate. So we take number U between 1 and plus infinity. Plus infinity is also allowed. And I claim that the Curtis space, the respective Curtis space, lambda nu of IP is nuclear even only if P satisfies the following condition. for every function sequence, generalized sequence P from P, there exists another sequence Q from P, and there exists a summable sequence lambda. So lambda sits in the little L1 space. That is non-negative. Such that Pi is less than or equal to lambda I Qi for all I. Let's observe that the result doesn't depend on nu. So if this happens for, say, nu equals to 1, then this is true for all nu between 1 and infinity. Well, here's a sketch of a proof. For simplicity, let's assume that I is a set of natural numbers. I is a set of natural numbers. And let's also assume that all Pi are strictly positive. Well, this is a special case, but the general case is easily reduced to this one. This is an exercise to reduce everything to this special case. Okay, now let's...
Сейчас, по меню только один раз встречается вообще формулировка. Что происходит?
Yeah, it's, the result doesn't depend on you.
What is new?
Nu is, well, it appears here. It appears in the definition of the Kyoto space. So formally, in the general case, these spaces are different for different infallibilities of nu. But it turns out that if lambda nu is nuclear for one of them, then it is always nuclear for all nu. And in fact, it will be clear from the proof that if it is nuclear, then all these spaces are the same for all nu. Well, I'll tell you more about this later. So anyway, to prove this result, let's consider this special case. And this, the key point of the proof is to consider this special case. And let's look at the following picture. So let X be our Kyoto space. So we again draw the same diagram as before. This is xp tilde. This is xq tilde. This is pi p. This is pi q. And this is pi pq. So the seminorms, the defining seminorms on X are indexed by the same Kyoto set, so it's natural to use them as indices for the seminorms also. So I claim, and this is very easy to observe, that every associated bounded space XP is actually isometrically isomorphic to the little L nu space. And the isomorphism is very explicit if xi is a sequence in X, in xp tilde. So let's observe that pi p is injective. So we don't have actually to take the quotient here. So xp tilde is just the completion of the space X for the respective norm corresponding to P. So this isomorphism multiplies xi by xi pi, by pi, xi pi. Now this is an isometric isomorphism. Okay, we have a similar isometric isomorphism here. L u. So we can consider this operator from L mu to itself. So what is this operator? I claim that this is exactly the diagonal operator, M P over Q. So a simple exercise is to show that the diagram commutes. Construct isometric isomorphisms, the isometric isomorphisms, which appear in this diagram, and show that the diagram commutes. And let's now recall one of the exercises from the previous lecture. So the diagonal operator from L nu to itself is nuclear, even only if P over Q belongs to L1. And this completes the proof. So we see that X is nuclear, even only for every P there exists Q such that this operator is nuclear, or equivalently such that P over Q sits in L1. But this is precisely what is written down here. P over Q sits in L1. So we have proved the quadratic pitch criterion in this special case, but the general case is reduced to this one. Okay, let's now continue our list of examples. Nuclear spaces. Example 2. The space little s of rapidly decreasing sequences is nuclear because it's a Kerr space, and it's very easy to see that this space satisfies the quadratic pitch criterion. For the same reason, the Kerr space S, or the space of rapidly decreasing sequences over z to the power n, also satisfies the same criterion, and so it is nuclear. Example 3. The space of smooth functions on the n-dimensional torus is nuclear because it is topologically isomorphic to this one. By the Fourier transform. Example 4. The space of holomorphic functions on an open polar disk in Cn is nuclear. Well, indeed, we have already observed some time ago that it is isomorphic to a Kerr space. And if we look again at the Kerr space isomorphic to this one, it's very easy to check that it satisfies the quadratic pitch criterion. So it is nuclear. For the same reason, if we take the space of germs of holomorphic functions at a point little z on the complex plane, and the space is nuclear. Because it is also isomorphic to a suitable Kerr space, satisfying the quadratic pitch criteria. To continue our list of examples, let's now prove a useful property of nuclear spaces, which roughly states that the class of nuclear spaces is stable under many natural constructions. So we have the following theorem. Part 1, if X is a nuclear remotely convex space, and Y is a vector subspace, then both Y and the quotient of X modulo Y are nuclear. Part 2, the locally convex direct sum of countably many nuclear spaces is nuclear. We have countably many nuclear spaces, then their locally convex direct sum is nuclear. Part 3, the product of an arbitrary family of nuclear spaces is nuclear. You have a family of nuclear spaces, then their product is nuclear. Property 4 generalize this property too, you have a locally convex space equipped with the inductive locally convex topology. Inductive locally convex topology generated by a countable family of linear maps by M from X and to X, where all the spaces Xn are nuclear, and such that the sum of their ranges covers X, then X is nuclear. Property 5 is about projective topologies. If X is a locally convex space equipped with a projective locally convex topology, projective locally convex topology generated by an arbitrary family of linear maps by I from X to Xi. Here the index set is arbitrary, where all the spaces Xi are nuclear. And we also assume that the intersection of the kernels of the maps phi I is trivial. This condition is often satisfied in many natural cases. Then X is nuclear. Part 6 is actually a special case of 4 and 5, namely a countable inductive limit, a countable inductive limit, and an arbitrary projective limit of nuclear spaces are nuclear. And property 7, the projective tensor product of nuclear spaces is nuclear. If X and Y are nuclear, then their projective tensor product and their completed projective tensor product are nuclear. Okay. Before we prove this result, let's prove useful lemma. Which roughly states that we can always assume, when working with nuclear spaces, we can always assume that the associated Banach spaces are Hilbert spaces. More exactly, if X is a nuclear local convex space, then there exists a directed defining family of 7 norms. Defining family P of 7 norms on X, such that all the Banach spaces X P tilde are Hilbert spaces. Or all P. Well, why is it so? We start by choosing an arbitrary directed defining family of 7 norms. Here, a directed defining family of 7 norms. And we modify it to the following way. We take the canonical map from X to XQ tilde P by Q, sorry, by Q. This is a nuclear map, so we can factorize it for a Hilbert space. For every Q, there exists a Hilbert space H. Continuous linear maps alpha and beta, such that PQ is beta alpha. Also, without also generating, we may assume that the range of alpha is dense in H. If this is not the case, we simply replace H by the closure of this space, and this will be also a Hilbert space, and we can draw a similar diagram for this space. So we will assume from the very beginning that this is true. And we now define a new semi-norm, as noted by P sub Q. This will be just the norm of alpha of X. Then it's a simple exercise to show that the Banach space X, P, Q tilde is isometrically isomorphic to H. Because of this quality and because of this property. So they are isometrically isomorphic, and on the other hand, if we now let Q run over BQ, we get a new family of semi-norms, P sub Q, where Q runs over Q, and we see that this is a directly defined family of semi-norms. They are continuous because all the maps alpha are continuous. On the other hand, every Q is dominated by the respective PQ because beta is continuous, and so this family is also defined. Okay, now we can prove our theorem. So part one, we have to show that a subspace and the quotient modular subspace of a nuclear space are nuclear. Let's take a continuous semi-norm P on X. Let P dot denote the restriction of P to Y. And let P hat denote the quotient semi-norm of P on the quotient. And the quotient will be denoted by Z. It's a simple exercise now to show that if we consider the Banach space associated to P dot, then this Banach space is isometrically identified with a subspace of XP field. Isometrically. And if we take the quotient, then we get there is an isometric isomorphism. Isometric isomorphism between the Banach space Z tilde P hat and the quotient of XP tilde over Y P dot tilde. This is almost immediate from the construction of all the three Banach spaces.
Сейчас, может, там не Полагаем, даже замкнутость пространства.
We don't assume that y is closed in X, but this one will be obviously closed in X tilde because this is a Banach space, and this is also a Banach space. So this isometric image of a Banach space is a Banach space. Okay, let's now draw a picture. This is, first of all, we choose now Q, the continuous seminorm on X, such that Q dominates P, and such that pi PQ, the canonical map pi PQ, is the nuclear. And we look at the following diagram. This is pi PQ. It acts from XQ tilde to XP tilde. Pi PQ. Here we have the restriction of this map to Y tilde Q dot and X and Y tilde P dot. That's denoted by pi P dot Q dot. Here we have the inclusions. And here we have the quotients onto Z Q hat tilde, Z P hat tilde. And here we have pi P hat Q hat. And the diagram commutes. And now we recall one of our earlier results. Well, first we recall the previous lemma. We recall the previous lemma, which states that from the very beginning, we may assume that all the spaces here are Hilbert spaces. So by lemma, we may assume that XP tilde, XQ tilde are Hilbert spaces. And now we apply one of our earlier results, which was about this diagram, and which stated that if you have a nuclear map between Hilbert spaces, and if you have a pair of subspaces, such that this subspace goes to this one, then the top horizontal arrow and the bottom horizontal arrow in this diagram are also nuclear maps. So this implies that pi P dot Q dot and pi P hat Q hat are nuclear. And that's it. So this completes the proof of part 1. So this implies that y and x modulo y are nuclear. Okay. Part 2. Part 2 was about countable direct sums. You have to show that a countable direct sum of nuclear spaces is nuclear. Okay, we take upon a space E, and we take a continuous linear map phi from the direct sum of the spaces xn to E. A continuous linear map. We want to show that phi is nuclear. Let phi n be the restriction of phi to the nth summand. So by assumption xn is nuclear, so phi n is nuclear. And so we can write phi n in the following form. Phi n is the sum over k. Here we have some numbers, lambda and k, some functionals f and k, and some vectors y and k, such that y and k is, y and k can be chosen in such a way that it is bounded by 1. Its norm is bounded by 1. F and k is equicontinuous in x and prime. Equicontinuous. And And we can choose lambda and k in such a way that the sum over k of their absolute values is less than 1 over 2 to the power n. This is always possible because n is fixed. So since this family is summable, we can multiply f and k by suitable numbers in such a way that this sum is as small as we want.
Excuse me, what is part 2 was about?
Part 2 was about that. Sorry, it's impossible to show it as not necessarily the proof. Part 2 was about that the countable direct sum of nuclear spaces is integral. So to prove part 2, we must show that every continuous linear operator from this direct sum from this direct sum to a bound space is nuclear. Phi n is nuclear, okay, so we can write it in this way. Now, f and k, so far f and k is defined only on the nth summand, but we can extend it trivially to the whole direct sum. Extend f and k to x, so x is our direct sum. We extend to x in such a way that it is 0 on other direct summands. F and k restricted to x m vanishes for all m different from n. And now it's a simple exercise to show that the whole family f and k over all n and over all k is still equicontinuous. It's equicontinuous. So for all n, we have chosen an equicontinuous family of linear functionals on xn, extended it trivially to the whole space, and then put them together in the whole family, and this resulting family is still equicontinuous. So it is equicontinuous, and now we can write phi. So each phi n looks like this. Therefore, phi is the double sum over n and over k, lambda and k, f and k, y and k. So f and k is equicontinuous, y and k is bounded by 1, and the sum of lambda and k is finite because of this estimate. And so we conclude that phi is nuclear. Yeah, if we substitute here a concrete element of the direct sum, then we have only finitely many summands. That's true. Anyway, it is nuclear. Okay, so this proves part 2. We're almost done. Oops. Part 3 is about products. We want to show that the product of nuclear spaces is nuclear. Well, let's take a bounded space. Let's take any continuous linear map from the product to x, to E. You can now recall how the standard directed defining family of seminorms on xi's looks like. We can easily deduce that such a map can be always factorized through a finite product. So there exists a finite set J in I and a commutative diagram of the following form. This is an exercise, but it is almost immediate from the definition of the topology on the product. Okay, but this one is nuclear by part 2. Because the product of finite and many spaces is isomorphic to their direct sum. This is nuclear by 2. And so this diagonal arrow is the nuclear map. And so this map is also nuclear. And this proves part 3. Part 4. Part 4 was about an inductive local economics topology of this form. But when we discussed inductive local economics topologies and when we discussed direct sums, we have already observed that in this situation, x can be identified with the quotient of the direct sum. X is a quotient of the direct sum of the spaces Xn. And it follows from the previous results that the direct sum is nuclear and the quotient of a nuclear space is nuclear. Similarly, in part 5, when we consider projective local economics topologies, projective local economics topologies, in this case, X can be identified with a subspace of the product. X is a subspace of the product of our spaces. But we already know that the product is nuclear and the subspace of a nuclear space is nuclear. So this gives us 5. 6 it was about countable inductive limits and arbitrary projective limits. But countable inductive limits, a countable inductive limit is a special case of construction 4, and a projective limit is a special case of construction 5. So 6 follows from 4 and 5. And finally, part 7 was about projective tensor products. Well, 7 follows from the next lemma, which is a simple exercise for you. And actually, we will need this lemma at the next lecture as well. Lemma states that if you have two local economic spaces, x and y, P is a continuous seminorm on x, and Q is a continuous seminorm on y, then there exists an isometric isomorphism between the following spaces, between the following bounded spaces. The first bounded space is the following. We take the projective tensor product of x and y, and we take the bounded space corresponding to the projective tensor seminorm on this tensor product. And the second one is the complete projective tensor product of the bounded spaces xp and yq. So these two spaces are isometrically isomorphic in such a way that the following diagram commutes. So here we have the canonical map by p tensor q, and here we have the tensor product of the maps pi p and pi q, such that the diagram commutes. Again, this is almost immediate from the construction. If we recall the construction of the associated bounded spaces, then we will easily see that this is indeed the case. But now, if you want to show that this space is nuclear, it's enough to show that these arrows are nuclear, but we already know that the projective tensor product of two nuclear operators is a nuclear operator. So this one is nuclear, and this completes the proof. Okay, so that's all for today. In the next lecture, we extend our list of nuclear spaces by using this theorem. In particular, we will see that the space of smooth functions on an arbitrary smooth manifold and the space of holomorphic functions on an arbitrary complex analytic manifold are nuclear. And the Schwarz space, or Rn, is also nuclear. I will also discuss some other nice properties of nuclear spaces.
Сейчас, мы это еще не знаем, мы же знаем, что они индуктивные пределы.
Индуктивный предел чего? Ну, в общем, да, мы почти знаем по поводу теоремы, но кое-что надо будет. Да, кое-что надо будет.
Сейчас, слушайте,